So I want to tell you a little bit about the periodic table. I know. It's okay. So the periodic table. So the periodic table that you have is it does change sometimes, and it changes because sometimes new elements are created. We have found all of the elements that naturally exist on Earth. Does anyone know where a new element might be created? Yeah?
In space.
Not quite. No. No. Not quite. In a piece of technology. You know what it is? You ever heard of a particle accelerator? Particle accelerator is a huge, huge loop of electronics and magnetism where they send atoms flying around at super high speed and they smash them into each other. And sometimes, for a brief period of millionths of a second, these atoms form a new element. But then it quickly is unstable and breaks out. But it still existed for this very, very brief period of time. And so some of those things are included on the periodic table. There's a very high mass materials like hafnium and meltrium and darwinium, rogentium. Those are some of those synthetic elements are known. But the original periodic table, as we know it, the roots of our periodic table were created by Dmitry Mendeleev, a Russian scientist living in Siberia, and he started to categorize and make this chart of the known elements. Here's what one of his original periodic tables looked like. Okay? And at the time of Mendeleev, when he was doing this research, there were only 56 elements that had been found on it. Okay? So he put them in this order and this pattern according to specific traits and according to their mass. And he had some areas like this where there's no element listed. It's just blanks. There's a bunch of them. And so what Mendeleev said was, he was predicting that we haven't found it yet, but somewhere on Earth, it's going to fit here. And it's going to have this atomic number and this atomic mass. It's going to have these properties. And guess what? He was right. We eventually found these elements that were missing, and they agreed very closely with what Mendeleev had predicted just based on creating this periodic table. I have a video about Mendeleev and the periodic table I'll show you later on.
Okay.
Yep. Now, some of you asked this question the other day, and I didn't answer it yet. So the atomic mass. So we said in atoms, what's the mass of a proton? 1. And a neutron?
1. Yeah,
Okay.
1.
So then, if the mass of those are 1 and electrons considered to be 0, why are all of those atomic mass numbers decimals? That's kind of weird. Well, it doesn't include the electron. There's another reason. So, if on your periodic table, if you see, for example, uranium down on the bottom, how many protons does uranium have? Way on the bottom. 92. Could it have 93 protons? No, because then it would be Neptunium. Could it have 91? No, that would be boracium. It always has 92 protons. That's the definition of uranium. However, is there anything else that might vary?
Thing up top.
Why would the atomic mass be different? No, the protons are always 1. But we're getting close. Another reason. Nope. That's going to be about the same as proton, but we're getting even closer.
Neutrons.
The amount of neutrons. The amount of neutrons in an atom can vary. So uranium typically has how many neutrons? No, neutrons. Minus 146. Could it have 147 and still be uranium? Yes. Could it have 145?
No.
Yeah.
Yes.
So the number of neutrons in an atom, it can vary. We call these atoms that have a different number of neutrons than usual isotopes. So an isotope is an atom that's the same element, but it has a different number of neutrons. For example, sorry, Elsa? Hold on.
So are like the elements that's the rest separated from like the rest of them on the inside, are they like the ones made by the particle or something?
Which ones?
The ones separated.
No, those are just because they wouldn't fit. If you inserted those where they should be, the arc would be really long because there's a gap. All right, so let me give you this example. Carbon. So if you look on your periodic table for carbon, how many protons does carbon have? 6. How many electrons? 6. Not enough. We're in the middle of this. Should I get one shot so you can go? How about neutrons? 6. That is the vast majority of carbon has that arrangement. 6 protons, 6 electrons, 6 neutrons. However, there's a small amount of carbon on Earth that's a little bit different. It's called carbon-13. It has 6 protons, 6 electrons, but has 7 neutrons. There is also some carbon we call carbon-14. It has 6 protons and 8 neutrons. So, hold on. A couple of things about, so we call these isotopes. These are 3 isotopes of carbon. They are versions of carbon that are slightly different. They have more or less neutrons. Now, carbon-12, which is the majority of carbon, is stable. Okay? And carbon-13, however, is unstable. It can spontaneously break down. Okay? Carbon-14 is very unstable. Okay? It easily breaks down. It's radioactive element. So, what is the atomic mass that's written on your periodic table? On your periodic table for carbon? 12.01. Why is it 0.01? There could be others, and the atomic mass listed is the average. So most carbon is carbon-12, but when you average all of it up, that brings the average up a little bit, and that's why all of those masses are decimals.
But like, there's some that has.
So on the homework for Mercury, at the top it was 88.1. That being one of the.
No, that's just the normal mercury. Yeah, why? Yep. Their whole numbers. Yeah, they may not have an isotope, or they may just work out to be anything. I'm not quite sure. All right, go ahead and let's do a couple of these as practice. So go ahead and fill in. Let's start with potassium, then we'll work our way through all the others. So go ahead and fill in all this information about the element potassium.
So what if you eat like a radioactive?
It might be that, but it's very rare. So probably it's not.
Like what aluminum?
So we use, this kind of aside, we use radioactive isotopes in medicine. Sometimes we give a person radioactive barium. They drink this liquid that has some radioactive barium in it. It goes through their digestive system, and then we can use like an X-ray, and because the barium is radioactive and releasing energy, we can trace the path it takes through their digestive system. It's called radioactive labeling. To see if there's a blockage in their intestine that you can't see with a normal X-ray. But if you give them this radioactive barium, we can trace the pathway it's taking and see if it's blocked somewhere. Sometimes it's done for coronary arteries. They can inject a radioactive dye into the arteries to get a picture of what they look like to see if there's a blockage in the artery. All right, go ahead. Did we do okay? Potassium? All right.
Oh.
Wow, no, we can do them. All right, so potassium, Olympia. What is its symbol? Its name? Its atomic number? Its atomic mass? Its number of protons? Neutrons? No? You got to carry the one or something. 20. Electrons? 9. Olivia. For the atomic mass, its atomic mass is 39.1, but when we're using that to calculate neutrons, we round it down. Okay, do bromine. Okay, Danielle, symbol. Name. Oh, shoot, I did the wrong one.
Al.
You did this one?
Yeah.
All right, aluminum.
13, 27, 13, 14, 13.
Good. Bromine. Wyatt. 45. We don't need it. Okay. I guess let's go back to the video, and you won't have to do. I guess you're not gonna have homework.
No homework? Yes, I have practice at 4:30.
You will have homework tomorrow. Don't get spoiled.